Hello, guys. Can you guys hear me? Good. Okay, so welcome to this session. We're gonna talk a lot about data lakehouse architecture and how to get data warehouse performance on the data lakehouse, and how fast performance doesn't only mean faster queries, lower response time or lower infrastructure costs. It also helps you with your data governance, simplifies your data pipeline, and those whatnot, right? So now let's get started. So first, data lakehouse. So what is a data lakehouse? We've been adding data warehouse-like features to the data lakehouse to open and standardized storage, right? Features such as schema evolution, compaction, near real-time ingestion, right? We're adding those features to open and standardized storage. So why are we doing that? The reason is, as opposed to, if you're using a proprietary data warehouse with the data that's stored in the format that is enforced by the proprietary data warehouse itself, right? The amount of workload you can run on that piece of proprietary data is limited by your data warehouse, limited by the capability of your data warehouse, right? But as opposed to storing everything in the open and standardized storage with the open catalog service, now we have a chance to unify most of our workloads, specifically batch and near real-time workloads on a single source of truth data. Unify everything on a single source of truth data. And that has a lot of benefits. First, it's great for data governance. There's only one copy of data you need to manage. Don't need to worry about different copies of the same data scattered in 15 different systems. And it's great, and it simplifies your architecture. Storage is expensive, it's stateful, right? Managing only one storage is really good, for your architecture. And also, you have the flexibility of, having one piece of data, but different compute engines on top, all of them being stateful, not persisting any data, swap them in and out with no problem, right? And overall, this is very cost effective. So data lakehouse is great, right? So people that are using lakehouse must be doing that, right? Unify all of their workloads on that piece of data. But the reality is, no, at least not yet. Users are still forced to copy their data out of the lakehouse because query engines are just not running fast enough. They're either not optimized for high concurrency, low latency workloads, or they're still on older technologies. They are not really taking advantage of all of the crazy optimizations we're doing to a query engine today in 2024, right? Not being able to handle those workloads means users basically has two options. So first, they either over-engineer, overspend on their existing query engines to get barely passable performance. And this is not really future-proof, and it's not really, sustainable, right? So if end up forcing users to copy their workload and their data to a proprietary data warehouse purely for query acceleration reasons. This does solve the query performance problem, but it brings a whole new set of challenges, right? First, you have to consider the cost of actually maintaining a infrastructure level software like a data warehouse. Use a lot of compute, it's stateful, right? It's very expensive to maintain. And also you have to consider the cost of the data ingestion pipelines, thousands of them, right? Writing your data from one file format to another, use a lot of compute, and it's very error-prone, very labor-intensive. And also you have to consider the challenge of actually designing a whole new set of schema, index design, matching the data type SQL between your lake layer and your warehouse layer. Just not anything we want to do. And most importantly, we're breaking the single source of truth data on the lakehouse. We're basically breaking the data governance promise, easier data governance promise as originally promised by data lakehouse, right? And that's not something we want to have. So what are the challenges? Why running fast queries on lakehouse that difficult, or people not doing that yet? So on a higher level, from existing query engines, query engines that are used for data lakehouse today are not really built for data warehouse-like workloads. Some of them are optimized for performance, but they're optimized for long-running batch workloads that runs that long ETL workload that runs for hours or even days. Stability, not low latency, high concurrency. Or they are optimized for something else instead of performance, right? Some of them are optimized to build great connectors that connects to 100 different data sources and get okay performance, but not low latency on the few, right, on the lakehouse. On the technical side, fetching data and metadata can easily become the bottleneck, on the technical side. First, you have to consider the I/O cost, actually moving data, moving the terabytes of scanned data, to your query engine. That takes a lot of network I/O. And that's even bad for query execution because it actually affects the data shuffling process, modern query engines still. And also you have to consider the slow and unpredictable performance of the storage device that data lake houses usually run on. Data lake usually run on, right? Like a cloud object storage, the response time can be upward to tens of milliseconds to 100 milliseconds. Not really acceptable for low latency queries, right? And also data metadata files can be unoptimized for query performance as well. This meaning, you have too many small files scattered around your S3. That's horrible for data scanning. Not really good for high performance, right? To address those challenges, so what are the features you should look for? If you do want to run high performance, low latency, high concurrency queries on the lakehouse, right? So first, a hierarchical caching framework is absolutely necessary, to overcome the unstable performance of data lake storage devices. And also to save I/O costs, actually fetching the data, that fetching process we're talking about. And also you want to find a MPP, massively parallel processing engine, that is able to do in-memory data shuffling, between memory data shuffling. Ideally running the entire query process in memory, which is more optimized for low latency instead of batch workloads, right? And also you want to find those that are written in the lower level language that are able to take advantage of all of the, SIMD optimizations. SIMD basically means multiple data points per CPU cycle. And that's great. That batch is great for OLAP, right? This is absolutely necessary. So actually with the right features and optimizations, getting data warehouse-like performance on the data lakehouse is not only possible, it's actually quite easy to do. It's quite easy to do. I'm gonna show you a bit. And we're gonna use StarRocks as the example here. I'm gonna talk about why in a little bit, but now a quick rundown of what it is. It is a query engine that has MPP architecture, C++ SIMD optimized. It's able to run data warehouse-like performance on the lakehouse, right? The reason why we picked StarRocks is that we want to do the comparison, right? StarRocks has two modes of deployment. One is as a data warehouse. It has its own storage engine, own table format, own file format. You can ingest into it and get sub 10-second data freshness on mutable data on its columnar storage. And that's great, right? As a data warehouse. Or you can swap the storage engine out with the lakehouse engine, with something like Delta Lake, with the Unity catalog, right? And you can run query directly against your Delta Lake managed Parquet files, basically, as a query engine on the lakehouse. So let's compare the two, right? So let's first set the baseline. StarRocks is really performant as a data warehouse. You can see the benchmark here, SSB benchmark test. So there are two versions of this benchmark test. One is a multi-table, which is original. It has all of the on-the-fly aggregations and on-the-fly joins. And the second one, the flat, is the single table, denormalized version, only having the on-the-fly aggregations, but not on-the-fly joins. You can see that StarRocks single table performance is so much faster than its competitors. But the key here is StarRocks multi-table performance is actually faster than Druid's single table performance. So joins for free, right? And almost as fast as ClickHouse single table performance. And this showcase, the performance StarRocks as a data warehouse, very impressive, right? And now let's compare the two. StarRocks as a data warehouse and as a lakehouse query engine on top of Apache Iceberg. Same exact hardware, hot queries, TBCDS, 1 terabyte benchmark test. The data warehouse solution is only 12% faster. You're only giving up 12% of the performance for what? For a chance to unify all of your workloads, your batch and near real-time workloads on a single source of truth data. Great for your governance, great for flexibility. And that's something that's amazing to have. And so how does StarRocks compare to other query engines? How does a purposely built lakehouse query engine compare to other? Here we want to use Trino as an example. Trino is a fantastic query engine for what it's really good at. It has an MPP architecture. It runs everything in memory. It's so much better than MapReduce. It brought the query latency from hours to minutes, right? And what I know Trino for is great connectors. And that's what users were asking back then, because we didn't really have a lakehouse architecture or a unified, strong storage that is able to take care of transactions, right? Schema evolution. So what users were asking was, I want to connect to all of my data sources and get okay performance. And they're written in Java, really optimized for that, writing great connectors fast, but not really optimized for performance for a few, like data lakehouses, right? And let's see the performance comparison. StarRocks is 4.6 faster than TPC than Trino on TPC. That's 1 terabyte. Than Trino, right? And this is even with Trino on the newer JDK version 21, supposed to be getting that SIMD boost, right? So this might sound pretty good in theory, right? Next slide. Sounds good in theory, right? But how is this being practiced in actual production systems by industry leaders? So here I want to introduce Eric Sun, a great friend. He's going to talk about Coinbase, real-time analytics, StarRocks, Unity Catalog, Delta Lake, and let's welcome Eric to the stage.
Thank you. So next slide, please. Hope everybody enjoyed the keynotes today, and there are like 2 words I want to just bring into our talk here. One is called impossible, because I think this talk is really going to show everybody some architecture that you can imagine something used to be considered impossible. We will show you that is actually possible here, right? The second one is really talking about the open, and open. We will show how Databricks is really building this ecosystem so that we can actually have one open data lake. Next slide. And you can put multiple engines on top of it. This is actually possible. All right, so I know there's some captions to cover the bottom. So that is the uniform and the Delta Lake. So I'm going to really spend a little bit of time to walk you through this architecture about how we use MPP engine in addition to Databricks, Data Lake, SQL, serverless, all the stuff for different use cases. And then in the center, you're gonna see the Unity Catalog, Data Lakehouse. But on the right, you're gonna see some little cute animals, both the puppy and the duck, right? And they all mentioned in the keynotes today, and we wanna see how we can put all these together, that you can really fulfill different business use cases using the best suitable engine with the single source of truth of your data. Okay, let's start with the left. So as a financial company, we need to do a lot of data analytics, such as crypto data, transaction data. And some of you probably hear a concept called operational data store. That's where you consolidate the data from multiple places, near real time, figure out the discrepancy. And in this case, you need some special engine. And you probably heard about Pinot, Druid, and even Trino or sometimes. But then why we work with StarRocks? Because it offers awesome features such as primary key, real primary key, not a pseudo index. It's a real index. It can enforce the dedupe, all the stuff. So you can continue to ingest your data real time, and they will do all the dedupe for you. They have an awesome feature of all kinds of a partition, list partition, range partition, hash partition, and co-locate data storage to make your join very, very fast. So in this case, you don't have to have this wide, big table anymore, like a ClickHouse or Pinot. You can just ingest the multiple stream into this area, and they can be joined on the fly without any delay. As Sita mentioned, there's a lot of technology like in-memory shuffle that will help you to improve the performance, right? That is the real-time part. But then our user becomes really into this system. They want more data, but we don't want to build a cluster with 100 nodes because it's gonna cost a lot. So thanks to Unity Catalog, we can offload the historical data to the uniform data lake with Iceberg and the Delta format. The data are prepared using Databricks, but they can be queried using StarRocks as a historical way, so that you can keep your StarRock cluster as efficient, as economically as possible, but then without losing the access to all your history data. So some of the use cases you can imagine, you can do feature generation, for risk, for anomaly detection. You can focus on the most recent data, but you can also do a wider lifetime value calculations using maybe 6 months or 2 years worth of data. And one MPP database can cover both, right? But this is just the beginning, right? As I said, there are some little cute animals on the right. So let me talk a little bit about what the other use case the open source Unity catalog will unblock for us. One is, for example, we have a lot of transaction data. We need to see a graph out of all this one and see who's trading with who and where's the clustering, what is the high risk. That's where we need a graph engine, right? Most of you probably heard about Neo4j, right? You started from there, but then when we try to load the history of entire Bitcoin and Ethereum, that database cannot handle the volume. So what we did is we used Unity Catalog to expose the same data from Databricks, which is real-time ingested from the on-chain, and then we can query them through PuppyGraph directly, without any transformation, without loading the data to another database, and we can actually traverse 8 hops of this graph within 20 seconds, okay? With terabytes of data in it, with billions of nodes and edges. So that's one use case. Without Unity Catalog, without all this open technology, it is impossible. But today, when you walk out this thing, you go back to your company, you can explore that because it is possible, right? Another thing, I don't need to elaborate too much. DuckDB, it's in the keynotes, it's so hot. So what I want to share here is we have a lot of Python users. They used to use pandas, they use NumPy, but they're single machine, not very scalable. Even DuckDB is also single machine, but then when we use DuckDB to connect to Unity Catalog, we can query our iceberg table easily. And we test this with up to 1 terabyte of data on a single machine. They can handle it very quickly. And you don't need to wait for the old Panda. You can still use Python to call DuckDB, and you can access all your fantastic data already existing on your lakehouse, right? And we start this integration with Databricks a little bit earlier. So if you look at the journey here, we haven't finished yet. We're still in V0. So our integration was not the official open source yet, but we just finished the authentication part so that we can use Unity Catalog to resolve all the table names to the S3 location. Then you can access them through your IAM row. That's where we are today. But then very soon, once the open source Unity Catalog API is published, we're going to switch to that one. We will get not only the authentication, but the authorization. And then you can see the journey will continue to move on to the Delta kernel eventually. So you can swap out some of the components in this diagram and imagine that you can use other query engines, which works the best for your business community and the data scientist or a machine learning team. And they can harvest all the golden data sitting in your data lake or lakehouse already. Okay? With that,
yeah, thank you.
back.
Thank you so much, Eric. Thank you. That was very insightful. And by the way, if you're into graph, PuppyGraph is right there. Waymo, set up. Yeah, if you want to talk to, if you want to learn more about GraphSQL, there's the guy. And thank you guys. And if you have any question, we do have a booth. Just look over right there. There's a blue digital data warehouse, booth number 75. You can come over and chat. And if you have any question, yeah, please. Now. Thank you. Appreciate that. Thank you. Thank you.